Hello everyone, welcome to this tutorial. In this tutorial we're gonna solve problems on magnetic circuits from problem set number 3. So let's start. Question 1. A conductor carries a current of 20 amp as shown in this figure. Find the flux density and the direction of the magnetic field at a distance of 5 cm from the center of the conductor. The conductor is perpendicular to the paper plane and the direction of the current is into the paper. So actually this question is a revision question from the magnetics principles. So we can use the magnetic principle to solve this question using Ampere's law. So the flux density is equal to mu naught I over 2 pi r, and we have all the data here to calculate the magnetic flux density. And of course, because the current is going into the paper, the magnetic flux will be clockwise. So that's all for this question. In question 2, we have a 100 turns coil is wound on a ring, has a 3 cm mean radius as shown in the figure below. The current through the coil is 10 amp. The magnetic field flux density in the ring is 0.3 Tesla. Find the relative permeability of the ring material. So here in this question, we know the current passing through the coil, the number of turns of the coil. We know the radius of this ring, and we know the magnetic flux density. So from the magnetic flux density, we know that it's equal to mu naught mu r times the current times number of turns over the length. This length is the length for the path of the flux itself. So here it will be 2 pi r. So here this length will be 2 pi r, and the only unknown in this equation is relative permeability mu r. So we can solve for mu r. And as you know, it's dimensionless. So that's all for this question. Question 3. The flux perpendicular to the cross-section plane of a 100 turns coil is given as a function of time. Find the RMS value of the induced voltage across the coil. So actually we all know that the induced voltage is the rate of change of the flux. So d phi by dt is equal to the induced voltage for one turn. So we should multiply that times the number of turns to calculate the total induced voltage. So that's very easy. It's just a derivative for this, and this is the negative sign from Lenz's law. And then we know the EMF as function of time. To calculate the RMS value, we know the maximum here, and this maximum over root 2 is equal to this voltage. Please be careful, because in the circuits, if we give you this voltage in time domain, we assume that this value is RMS value, but here it's assumed to be maximum. Okay, because we calculated this EMF from the flux. So this is a maximum value, and then we should divide over root 2 to calculate the RMS value. For the next question, a ferromagnetic rectangular core with a mean circumference of 36 cm and a cross-sectional area of 3 cm squared is wound with 400 turns of wire. when the excitation current is 1.4 amp. The flux is found to be 1.4 milliweber, and it's required to calculate the reluctance of the ring and the relative permeability. So in this question, we know the mean circumference for this rectangular core. So actually, we know the length for the path of the magnetic flux, and we know the cross-section area, we know the number of turns, and we know the current, and also we know the flux. And we need to calculate the reluctance and the relative permeability. For the first part, the reluctance is equal to Ni over phi, because this reluctance times the flux is equal to the magnetomotive force, which is also equal to the number of turns times the current. So because we know the number of turns and the current and the flux, we can easily calculate the reluctance of the ring. But in order to calculate the relative permeability of this iron, we will use another equation for the reluctance, which is the reluctance equal to the length over mu naught mu r times the area. Here we know the length, the area, the reluctance is calculated from the first part, so the only unknown here is mu r. Here. So that's all for this question too. Okay. A magnetic circuit with a single air gap is shown in this figure. The core dimensions are cross-section area is given, the mean core length is given, so the length for this core, the mean length is given, and the number of turns is given. Assume that the core relative permeability is also given. Neglect the effect of fringing field and the leakage flux. Calculate first the reluctance of the core and that of the air gap, and the total flux for a current of 1.5 amp. So in order to solve this question, we need first to draw the equivalent circuit. So in order to again solve this circuit, we need to draw the equivalent circuit. So here we have a source for the magnetic flux, which is a coil here, and so this coil produces a flux, and this flux is passing through the core and the air gap. So we have a source and we have a core and air gap. So this source is modeled as a magnetomotive source, and we have two reluctances, not resistances. We have two reluctances, one for the core and one for the air gap, and we have flux passing through this loop. So this is the equivalent circuit for this magnetic circuit, and this source is equivalent to the voltage source in the electric circuits, and this reluctance is equivalent, or is the map of the resistance, and here the flux is the map of the current. So we can use the electric circuit's law now on this circuit. But before solving this circuit, we need to calculate first the reluctance of the core and the reluctance of the air gap. So the reluctance of the core is equal to the length over mu times the area. Here we have the mean length for the core, so the length is given. We know the area, so, and we know mu r, and mu naught is a constant, we know it. So we can calculate the reluctance of the core. Now, in order to calculate the reluctance of the air gap, we need again to calculate to know the length of the air gap and the area and the cross-section area. We have the length of the air gap here, it's given, and it's the same cross-section area, because we are neglecting the effect of the fringing effect. So we know the length and the area, so we can calculate the reluctance for the air gap. Now, in order to calculate the total flux for this current, now we need to go to the equivalent circuit. We know these two values, we know these reluctances. We know the voltage source because we know the current and we know the number of turns. So we can easily calculate the flux. The flux is equal to this source over these two reluctances in series. So this source is N times I. All these values are given. And we already calculated the reluctance for the core and the air gap. So we can now calculate the flux. For question 6, the core shown in the figure below has a mean length of 26 centimeter and cross-section area of 4 centimeter square. The material is sheet of steel with mu r, so we have the mu r, and coil A carries a current of 0.8 amp. This is coil A. Coil B carries a current of 0.6 amp. This is coil B. And we know the number of turns here, 400 turn, and here 300 turn. Now determine the flux set up in the core. Again, in order to solve this circuit or any other magnetic circuit, we need first to draw the equivalent circuit. Here we have two sources and we have one core, so we have two sources and one reluctance. So we have two sources and one reluctance. But be careful, because the direction of this source now is tricky, because we have two sources. So either the total will be A plus B or A minus B. So you have to take care of the direction. So now go and use the right hand rule to determine the direction of the flux generated here, and you'll see that it's positive at the top, negative from the bottom, and here it will be positive on the right and negative to the left. So now the equivalent here will be A minus B if you take A as a reference, or B minus A if you take B as a reference. Okay, now we draw the equivalent circuit. The value of the magnetomotive force for coil A is equal to the number of turns times the current, and these values are given. Also for coil B, it will be equal to the number of turns times the current. And the only unknown now to calculate the flux is the reluctance of the core. So the reluctance of the core is equal to the length over mu times the area, mu equal to mu naught times mu r. So here we have mu r and mu naught, length and area, to calculate the reluctance. As I told you, the magnetomotive force for A and B is equal to the number of turns times the current for each coil. And now that flux is equal to flux A minus B. Now we are assuming that A is the reference over the reluctance, and the value is positive, which means that yes, A is the dominant here. If you calculated B minus A and you found a negative value, so you will see that the direction of B is wrong. And that's all for this question. Question 7. A two-legged core is shown in the figure. The winding on the left leg has N1, this winding, has 600 turns, and the winding here has 200 turns. The coils are on the direction shown in the figure. If the dimensions are as shown, then what flux would be produced by currents I1 equal to 0.5, I1 is passing through coil 1, and I2 equal to 1 amp, and this current is passing through coil 2. Assume relative permeability of 1000. So again, in order to solve this circuit, we need to draw the equivalent circuit. In this question, we have two coils and one core, so the equivalent circuit will be exactly like the equivalent circuit for question number 6. We will have two sources and one reluctance. For each source, you can calculate the magnetomotive force by multiplying the number of turns and the current, which is given for each source. And we can calculate the flux if we know the value of the reluctance. So now we need to calculate the reluctance. And the tricky part here, that the mean length for the reluctance is not given. So we need to calculate the mean length. So I will start with this point here, and we will have 7.5 centimeter to this point, and then 50 centimeter to this point, then another 7.5 centimeter. And this length is repeated for this leg and this part, and here too. So we can multiply this length times 4 to calculate the mean length. But be careful, because you have to convert all your data to the meter for these data and for the depths too. So we have here the area, which the cross-section area, which is 15 times the depth, which is also 15, and you have to convert this centimeter square to meter. For the length, we'll have 7.5 plus 50 plus 7.5, all this multiplied times 4, and then we again have to convert this length to meter. Now we have the length and the area, we can calculate the reluctance, then we can easily calculate the flux. So that's all for this tutorial. Thank you and see you next.